Yeah, so hi, my name is Jacqueline Vinden, and I am a recent graduate from Dr. Pat Fraser's lab at McMaster University. I'll be going over some of the finds from my master's thesis, where I focused on monitoring water quality for recreational use in the nearshore waters of Eastern Georgian Bay. So I'm sure everyone here knows, Georgian Bay is known for its excellent water quality, which is very important for the lifestyle, economy, and ecosystem health of the numerous townships throughout Georgian Bay. And one of the important ways to protect this important or this excellent water quality is doing consistent monitoring to understand what the current water quality conditions are, how they've changed over time, and what the potential drivers for these changes are. And so that's what I'll be focusing on for my study, but I focus it in on the township of Georgian Bay, which is on the southeastern shorelines of Georgian Bay, outlined in purple there. And so the township of Georgian Bay really only had one comprehensive study that was conducted recently that looked at both fecal bacteria and nutrients, and that was conducted by Schaefer and Schaefer between 2001 and 2009. So that's over a decade ago, and that's pretty significant because since that time period, there has been increased year-round use of existing cottages, as well as increased recreational development, including a residential and golf course development in Oak Bay. And so these have been shown to impact water quality, but there also has been increased water levels of about 1 meter between 2009, which was a sustained low water level period, and 2020, which had record-breaking current water level. And again, that also has been shown to affect nutrient concentrations in wetland and could impact the water quality. So with that, my project was to resample sites within the township of Georgian Bay that were sampled between 2001 and 2009 for both total phosphorus and E. coli. So I have two main data sets that I used for my project, an historic one and a current one. And the main data source for my historic data set came from that comprehensive study that was conducted by Schaefer and Schaefer. So between 2001 and 2009, they sampled over 100 sites along both the nearshore waters of the township as well as in some of the inland lakes. And they sampled for both E. coli, since it's a fecal bacteria and can be used as an indicator of pathogens, as well as for total phosphorus, since it's a primary nutrient and is generally a limiting nutrient in fresh water. So they sampled for E. coli between June to September, about 5 times at each site. And they sampled for total phosphorus only once in early to mid-September at each site. But for both of these colleagues, they found that the background levels in Georgian Bay were less than 10 colony-forming units per E. coli, or 10 micrograms per liter of total phosphorus. Now, in terms of the current data set, the PCF lab sampled approximately 60 of those historic sites, as well as approximately 20 new sites between 2020 and 2022. And they sampled for both E. coli and total phosphorus in the months of June to September, at least in monthly intervals for the latter 2 years. And at each of these sites, we collected samples in duplicate, one to look at E. coli and one to look at total phosphorus. We also measured turbidity as well as other limnological variables like specific conductivity. And then at the end of the day, we used one of the containers of water to enumerate E. coli using the detective B16. And then the other container was frozen and brought back to McMaster University, where it was enumerated for total phosphorus concentrations using the molecular method. So then this leads me into my chapters for my master's. So I had 2 chapters. The first one was to look at the regional drivers of water quality impairment in the nearshore waters of the township. And the second one was called the periplate, a novel way to track nutrient status in nearshore recreational waters for volunteers. So I'll first talk about my first chapter, where I had 3 main goals. The first one was to determine the long-term changes in E. coli and total phosphorus between the 2 decades. The second one was to identify any current areas of concern. And the last one was to understand what the potential factors could be that will be influencing any regional variations to see. Before I go into that, I'll quickly go over the water quality guidelines so we're all on the same page with these. So Health Canada in 2022 created a new guideline for E. coli called the Beach Action Value, or BAE, which is 235 colony-forming units per 100 milliliters of water in a single sample. Unfortunately, they don't have, or Health Canada doesn't have a guideline for total phosphorus. However, the Ministry of the Environment in 1998 created some guidelines where they recommend that to avoid use of pollutants, total phosphorus concentration should be less than 20 micrograms per liter. And to protect against acidic deterioration, which is what we would be interested in, TB concentration should be less than 10 micrograms per liter. And then Schaefer and Schaefer in 2010 created the Georgian Bay water quality objective based off of the background levels they found during their research. And they suggest that for both E. coli and total phosphorus, concentration should be less than 10. Now, before I could do any comparisons across time periods, we first had to standardize the data sets. And that's because they were taken during different years in different weather using different methods. And so the first thing that we looked at was to determine how rainfall intensity impacted the level of colloids in the water. And so we selected sites that were sampled in at least 3 different rainfall intensities, with 0 having no rain and 3 having heavy rain. And we found that rain does lead to an inflation of total phosphorus in E. coli. And so moving forward, we'd only be using fair weather data in our comparisons. The next thing we wanted to look at was to see how monthly variation impacted pollutant levels. And that's because the water is taken, or samples were taken during different months. So we looked at sites that were sampled at least once during the 3 peak summer months of June, July, and August. And we found that there was no monthly differences between mid-June and early September. So we'll therefore be using data collected from days 170, which is mid-June, to 2 June. And then lastly, we had to compare the methods, and that's because historically, Schaefer and Schaefer used the coli plate to enumerate E. coli, whereas currently we use the Tecta B16. And we found that there was a significant relationship between the Tecta and the coli plate, and we used that equation and relationship generated to correct the results so we could compare them. Now lastly, I just wanted to go over the regions and focal areas before getting into the results, as it is pertinent to some of the results I'll be talking about later. And so there are 6 regions within the Tasman Georgian Bay, with 12 Mile Bay in the north and Oak Bay in the south. However, only 5 of these species were sampled historically by Schaefer and Schaefer, and those were 12 Mile Bay, Mawatamazi, Go Home Bay, Conalsheen, and Hunting Harbor, and then Oak Bay was added in 2020. And then within each of these regions, the focal areas, which we delineated based on shared spatial characteristics, so things like site, location, cottage density, and recreation development. And so in total, there are 6 regions and 13 focal areas. So now getting into some of the results. So for our first goal, which was to determine the long-term changes in E. coli total phosphorus concentrations across the 2 decades, when looking at E. coli, we selected sites that were sampled at least twice during each period, with period 1 being the historic period and period 2 being the current period. And we found, well, there's 36 sites that matched this criteria, and we found that over 80% of the sites had a decrease in E. coli concentrations from period 1 to period 2. And this can be exemplified looking at this first line here. You can see that in period 1, 0% of the sites had E. coli densities that were less than 10, versus in period 2, 81% of sites had E. coli densities less than 10. You can also see that in period 1, 6% of sites had E. coli densities over 100, where no sites in period 2 had E. coli densities over 100. And you can also see that in period 1, 4 sites exceeded the beach action value, whereas only 2 sites exceeded the beach action value of period 2. Unfortunately, there are only 2 sites that met the criteria for inclusion in the study in terms of total phosphorus, and those were Cow Island in Inner North Bay and Hunting Harbor. But for both Cow Island and Inner North Bay, we did see a decrease in total phosphorus concentrations from period 1 to period 2. So with this, we're able to conclude that generally there has been a decrease in E. coli from the historic to the current period. However, this is most likely related to a dilation factor associated with higher water levels. So again, as I mentioned at the beginning, there has been a 1-year increase in water levels. This means there's more water, greater volume of water in the bay, which then can lead to a dilation with all its pollutants. So moving on to the second goal, which is to identify the current areas of concern for E. coli and total phosphorus within the township. To do this, we selected sites that were sampled at least twice in the current period and calculated the mean for those over the current period, and that's what's shown in this map here. So you can see for both E. coli and total phosphorus, the majority of sites are below that Georgian Bay water quality objective of a 10, but there are definitely some sites that consistently had higher levels of E. coli or total phosphorus. You can see that that's Bloody Bay, Frey's Channel, the Sand Run in Morris Bay, as well as quite a few sites within Hunting Harbor and Oak Bay. When comparing E. coli densities across regions, we can see that Hunting Harbor had the highest mean E. coli out of all of the regions, followed by 12 Mile Bay and Oak Bay, and then Oak Bay had the greatest percentage of sites that exceeded the Georgian Bay water quality objective, followed by 12 Mile Bay and Hunting Harbor. We also said Hunting Harbor had the greatest number of sites that exceeded the beach action value. And when looking at total phosphorus, it's a similar story told there. We can see that Oak Bay had both the greatest or the highest mean total phosphorus out of all the regions, as well as the greatest percentage of sites that exceeded the Georgian Bay water quality objective. followed by Honey Harbor and 12 Mile Bay. We can also see that Honey Harbor had the greatest number of sites that had TP concentrations that were above 2 micrograms per liter, which is known to be a trigger point for eutrophication. So with that, we're able to conclude that generally on a regional basis, Honey Harbor and Oak Bay have higher pollutant levels than other tasting. So then moving on to a third goal, which is to understand what potential factors might be influencing these regional variations. We first had to decide what potential factors we wanted to look at, and we narrowed it down to looking at cottage, dock, and road density, as well as modified land and commercialized land. And that's just based off of the data we had available as well as the literature. And just modified land use really refers to anything that's not natural. So things like marinas, parking lots, lawns, trailer parks, and then the commercialized land use is a subset of the modified land use, is just referring to anything that's based in commercial property. And the reason we are focusing on these, on road density and modified land use specifically, is because it leads to an increase in impervious surfaces, which reduces the natural filtering that occurs as water flows over natural land. And it also increases the rate of runoff. So you'll have a greater rate in amount of runoff with a higher concentration of pollutants in it. And that can be exemplified in this diagram here, where you can see that when you have an increase in pervious surfaces, or those natural surfaces, you have a smaller amount of surface runoff compared to impervious surfaces, and you have a greater amount of those, you have a greater amount of surface runoff. And also when you have more roads, it allows for greater accessibility, which can lead to increased development as well as more cottage use. And this can lead to increased stress on septic systems. So for those who are unfamiliar with how a septic system works, the sewage from your house will enter into a septic tank where the solids and liquids will settle out, and the liquid will enter into a drain field where it will filter through the substrates, so like things like sand or gravel, and then that water, that clean water will then enter into the groundwater. And this is very current within the township of Georgian Bay, since the majority of cottagers in homeowners rely on septic systems to treat their waste. And this can be problematic if the septic tanks aren't maintained properly. There can be leakages, as well as if the septic tanks are a bit older, they might not have the same capacity that is required for the use of that Connie just had here. And that can lead to raw sewage directly entering into the water. And then also with the increased water levels, it can lead to the drain fields being flooded out. And that would mean that raw sewage, again, is directly entering into the bay. And so in order to look at these, we calculated the potential drivers for each of the focal areas. And we noticed a trend with the 6 most northerly focal areas, so from Con Machine up, having lower cottage and dock density, generally zero road density, except for 12 Mile Bay does have some roads, and then a lower percentage in modified area compared to Honey Harbor and Oak Bay that had high cottage and dock density, high road density, and a greater percentage of modified area. So when you compared these and correlated with them with the mean E. coli and D total phosphorus for each of these local areas, we saw that both mean E. coli and mean total phosphorus had a positive and significant correlation with road density, and that mean total phosphorus and mean E. coli had a positive correlation with the proportion of modified area, but only mean total phosphorus was significant. So with that, we're able to conclude that E. coli and total phosphorus are significantly and positively correlated with road density as well as the proportion of modified area. And so with that, we have a few recommendations for the township based on those findings. The first one is to continue sampling for E. coli and total phosphorus, but to really focus it in on those problematic areas like Honey Harbor and Oak Bay. We also recommend that they conduct microbial source tracking to determine the origin of E. coli. And that's because E. coli can come from numerous different sources, including wildlife and humans. And depending on where that source is, it's going to impact the policies or programs that are created, as well as have different impacts to human health. We also recommend that they use strategic sampling both during and after storm events. So that's because storm events lead to a greater amount of E. coli or nutrients in the water. So you can use that to better determine the source of where it's coming from. We also recommend they reduce and limit development, especially around those areas that are boat access only, as those are shown to be a driver of these pollutants. And then to also naturalize existing shoreline areas so there is more of a buffer so that some of that natural filtering can occur. And lastly, to ensure that the septic systems of the residents are maintained and functioning properly, and we believe that those are a source of E. coli. And then quickly, I'll go into the second chapter, which was to create a novel method for determining nutrient status in the nearshore waters that can be used by the community. And there's two main reasons we wanted to look at this. The first one is because those more traditional methods that I was talking about before They're not always accessible for a lot of communities to use over a long-term basis, since they require a lot of time to do the amount of sampling you need, as well as a lot of resources. So we're hoping that we can create something that communities can use to monitoring the water themselves. And then also we found that when you're taking grab samples of total phosphorus, it's really dependent on where and when you're taking them. So you might just miss those nutrients in your grab sample. And we're hoping that this method can show more of the nutrient status over an accumulation of time. And this can be done kind of looking at these pictures here. So these were taken by Schaefer and Schaefer in 2010 in Port Severn. And you can see that looking at this, the water quality is not looking that great. There's a lot of algae. So you're going to assume there's a lot of nutrients in the water as well. However, when they did a grab sample, they found that the nutrient concentrations, or the TP, was only between 13 to 15 micrograms per liter. So even though it is above the Georgian Bay water quality objective, it's not quite as high as you would expect for water looking like this. So with that, our goal was to develop and test a novel method to track changes in nutrient status and the nearshore water quality using periphyton that is accessible to most communities. So we created something called a periphyton meter, which is a 3D printed slide boulder that can suspend in the water. And the goal of it is to measure periphyton, which is the algae seen in this picture here, and it's the green algae that grows on substrates at the bottom of the water. And the reason we're focusing on looking at periphyton is because it can respond quickly to changes in the environment, including total phosphorus. And it is cost-effective, it's easy to use, and has been used effectively to monitor agriculture through disturbed streams as well as wetlands in the past. So to use it, you would suspend the periphyton meter at a certain depth so that it's exposed to ambient light as well as nutrient conditions. And then you would leave it in the water for about 2 weeks so that the algae can grow on it. And then you scrape the algae off and you use chlorophyll to extract, or use acetone to extract the chlorophyll, which you can then relate to the periphytic biomass. So last summer in August, we ran a pilot program to determine the periphyton meter sensitivity to different levels of human disturbance. And so we placed 2 periphyton meters in areas that had a more high recreational development, so directly within an arena and then along a busy boating channel. And then we placed 3 in areas of more low human disturbance, so along a rocky shore, amongst the dock of a cottage, and then in a wetland. And we found that the areas of high human disturbance had significantly higher periphytic growth than the periphyton meters in the areas of low human disturbance. And that's exemplified in the green bars on the bottom. But we did find that there was no correlation between total phosphorus and periphytic algae, which could be explained by the fact that TP, again, is really showing you that instantaneous nutrients in the water at the time of the grab sample, whereas periphytic chlorophyll, since it's in the water for 2 weeks, is showing you an accumulation of those nutrients over time. And that can be exemplified when looking at the wetland site, so the one on the far right, where you can see that it had the highest amount or highest concentration of total phosphorus, which is expected when looking at wetlands, but it didn't have the highest growth of periphyton. And that could tell us that that total phosphorus is being uptaken by the macrophytes of the plants in the wetland and is not actually readily available in the water column for algae to grow in. So it can help give us a different perspective on the water quality than just when you're looking at those grab samples. So with that, we're able to conclude that the periphyton meter results are sensitive to areas of high community disturbance and may be useful in a long-term monitoring program moving forward. So with that, I have 4 main conclusions from my thesis. The first one is that E. coli and total process concentrations have generally decreased over time, which is likely due to the dilution factor associated with the higher water levels. This is important as the water levels are predicted to decline over time. We might be seeing an increase in these E. coli and total process concentrations in the future. We can also conclude that Hunting Harbor and Ilfay are the problematic areas compared to other regions, and that more intensive sampling should be focused in those regions than other ones. We can also conclude that E. coli and total phosphorus are positively correlated with river density, the proportion of modified area. And that lastly, the periphyton meter may be a useful tool to track changes in nearshore water quality and could be implemented in a long-term monitoring program, which is something we'll be doing this summer and testing different ways for that to work and hopefully running one in August. So thank you. I wanted to say a huge thank you to Mary, the Georgian Bay, and everyone here for being here to watch this and learn about it, for helping me with my project and making it possible. And then also a huge thank you to Pat for supervising our project as well. And to Edward us on the screen, since there's so many people.